Okay, hi, welcome back on this second part of the video where we try to understand why space-time should be curved by massive objects. So in the first video, here, in the first video, we saw that you could measure the proper time of someone going at relativistic speed. So you could measure the proper time of someone detail if you know if you measure its velocity over a period of your own time t by the relation 1 minus the velocity that you measured squared over a period of your own time. So this is a very important relation, and we will now see different cases. Okay, so this was the first video. Oh, sorry, it's a square root here. Okay. Case one, the velocity is constant, which means that the velocity is not a function of time. So this is your space-time diagram where I now consider only the x spatial direction and an object going at constant velocity through space-time. Its world line will be a straight line like this. So you see that, let's say, for an hour, you travel maybe, I don't know, 300 kilometers if you go at 300 kilometers per hour. Yeah, so that's just an example, but I think we're far from relativistic speed, but okay. That's what the world line of an object going at constant speed in space-time would look like. And the slope of this curve is 1 over v, the constant velocity. Okay. Now let's say that this object is now here in space and time on his world line. So at this point P, I can project my space-time axis here to understand better that at point P, this is x and t, and we see that we have an angle here. And now I want to go in the rest frame of, let's call it, okay, let's say it's Paul going at velocity v, and now I want to go in rest frame of Paul. So go in the rest frame of Paul. This, we do it mathematically by applying a Lorentz boost, which is a rotation of space-time under which your line element ds square is invariant. And so I want to go in rest frame of Paul. So the flow of time is given by its unit tangent vector u. So I know that the unit tangent vector is always directed toward the future. So I know that his proper time is going like this. This is how the proper time of Paul goes by. And by the Lorentz boost, I now obtain the line of simultaneity here, which could be his proper space. So this is proper time, and now this is his proper space, but that's what we call the line of simultaneity. And I'm going to explain. Yes, we call it the line of simultaneity because you see that before here, if you were, I don't know, if this is, if 3 hours have passed from 0 now, if this is 3 hours, for everyone on this line, so for everyone in space on this line, 3 hours has passed. So this is the line of simultaneity, meaning that everyone in space will measure 3 hours here, 3 hours here, 3 hours here, 3 hours here. They will all measure the same time. Time is constant along this line of simultaneity. But now, because we apply the Lorentz boost to go in Paul rest frame, the line of simultaneity seems tilted. Okay. And so if his proper time slope is 1 over v, his proper space slope is v, and this I can call delta x, this delta tau. Wait, it's not really clear what I'm doing here, so I'm gonna do it again. Line of simultaneity or proper space. Okay. Yes, we know that the slope of the slope of a trajectory it's f of x divided by x, or sorry, or y divided by x. Okay, this is how we define the slope. It tells us for how much you go up, or how much for this distance, how much you will go up. That's the slope. Okay. And here the slope of the line of simultaneity is v because it's it's the inverse of this slope. But if I project the delta tau axis here, I can say that it's also this distance delta x divided by this delta tau. So now I still have v equal delta tau divided by delta x. And this is useful and we will come back to it. Okay, but that was the case of v constant. And now we need to go to an accelerating case. So v is no longer a constant, v is a function of time. And it's increasing or decreasing, acceleration or deceleration. Okay, so now case 2. Sorry, my pen is again not working. Okay, case 2. constant acceleration. Constant acceleration, A. I call A the constant acceleration. I'm sorry, my pen does not want to work. Oh, still don't want to work. That's great. I love it. All right. Okay, now it's working. Sorry for that. So case 2, constant acceleration. Yeah, and I had something to add here. So when we go in the rest frame of Paul, we apply a Lorentz boost. And in the rest frame, it's the frame where Paul doesn't move. Because you have to understand that actually you're never moving really in space-time. I mean, you are, but from your point of view, in your rest frame, you never are. It's always the world around you that is moving. I mean, when you are in a car, sure, the car is moving on the road, but you in your rest frame in the car, it looks like it's the landscape that is moving from your windshield to your back rear. I mean, it looks like the landscape is moving and you're just sitting on the seat of your car and you're actually not moving. So in your rest frame, you're never moving. And that's what the Lorentz boost is doing. It's going in the rest frame of Paul, where the velocity of Paul, u, the component of the velocity of Paul are 1, 0, 0, 0. Paul is not moving in space. That is x, y, z coordinate or component, sorry. And yeah, in the rest frame of Paul, he is not moving in space, is fully moving in time. That's what is meant by going in the rest frame of Paul. And I needed to add this point that in your rest frame, the world is moving around you, but you're not. Okay. It's just a matter of point of view. Okay, constant acceleration A. So once again, we want to draw a space-time diagram. So T, X. Okay, and now I will ask you to consider a rocket accelerating. So a rocket accelerating, that's the windshield of the rocket. That's the jet of the rocket. We have one clock close to the jet that we call clock A, and we have one clock close to the windshield that we'll call clock B. Of course, compared to the universe, those two clocks are very, very close to each other, and it's important that they are close to each other because we want their proper time to have the same graduation. In the first video, we saw that we could graduate word line with proper time. And so now if I draw the word line of clock A, it will look like something like this, and word line of clock B will look like something like this, and we want them to have the same proper time graduation. All right. So it is very important in my argumentation now, in my derivation, that those two clocks are close enough to each other. Okay, now let's say that you want to compare clock A and clock P at this point on the word line of clock A. So at this point P on the word line of clock A, you want to compare the time of clock A with the time that is displaying on clock B. So once again, we need to apply a Lorentz boost to go in the rest frame of clock A. If I project my axis, we see that we have an angle here, and the Lorentz boost in the line of simultaneity is given by this. Then I need to have the same angle here. Okay, and now with this diagram, it is pretty obvious that, and I usually don't like when teachers say that something is obvious, but now we see that tau A is shorter than tau B, or tau B is longer than tau A. So this is the line of simultaneity. At point P on the word line of the clock A. And when you're going to compare clock A with clock B, it will seem that more proper time as goes by for clock B. Because of, as a result of the Lorentz boost. Yes. Let me just write that down. So we see that tau A smaller than tau B, which is to say that in the accelerating rocket, clock A seems to tick slower than clock B, or the clock B seems to tick faster than the clock A, because along this line of simultaneity, which is the line on which you will do in any of your measure, clock A is shorter than, I mean, the time on clock A is shorter than the time on clock B. Yes, so seems to tick slower than clock B. And now we can go back to our first case where we've seen that the slope V here can be described as delta tau A over delta X. I mean, sorry. Yes, delta tau. Okay. So we now see that if you do tau B minus tau A, you obtain this small delta tau here. If you do tau B minus tau A, you obtain this small delta tau here. Delta tau, let me write that better. Delta tau, okay. but delta tau, we can relate it to the slope of this line of simultaneity because we saw that V equal delta tau over delta x, which is to say that delta tau equal V delta x. And also V, you can approximate the velocity of the ship as its constant acceleration a times the time that has passed, the proper time of tau a, how much tau proper time has passed at tau a, because we're doing a measure on the world line of the clock a at point b. You can approximate the velocity of the ship as the acceleration, constant acceleration time, how much proper time has passed for clock a. And this you can see it with a more classical example that if you are accelerating at constant acceleration 10 meters per second square, if you want to know what will be your velocity in 30 seconds, so v at t equal 30 seconds, what you can do is 10 times 30, and you can approximate that in 30 seconds. If you have a constant acceleration of 10 meters per second square, your velocity will be of 300 meters per second. So this is now A, and this is now 2A. So that's the classical point of view. Now we are in relativistic, so we can only do this approximation. And so we see that tau B minus tau A is equal to delta tau, which is V delta X, but V is A tau A delta X. Yes, this is V, A tau A. And now with some algebra, I can just factorize that out. 1 plus A delta X. So tau B equal tau A 1 plus A delta X. And this is a very important result here that gets us one step closer to understand why should space-time be curved by massive objects. Okay. So now, final steps. I think I will do it here. Final steps. So we were in a constant accelerating frame. And now we have to use the last ingredient to the recipe to go from accelerating, that should be a E here, accelerating frame, to go from an accelerating frame to gravity field, we have to consider the equivalence principle. The equivalence principle is a principle that is valid only in small regions, exactly like I did here, when you can graduate both world line with the same proper time graduation. So yeah, the equivalence principle holds for small regions enough of space-time and tells us that no physical experiment can be done to show, so no experiment can show if you are in an accelerating rocket or on Earth in our case. Given that the acceleration of the rocket is the same as the acceleration we experience on Earth, then no experiment can show if you're in accelerating rocket or on Earth. Yes. Or for example, if you are free falling, or if you are very far in outer space, very far from any gravitational field, so you are sort of in the interstellar space, then no physical experimentation can tell you where you are. So if you were blind, you will not know the difference between uh, being in a free fall or being in outer space. And same here, if you have no windows in your rocket and no windows in your laboratory on Earth, you cannot know if you are in an accelerating rocket or on Earth, given that the rocket would accelerate as the same gravity acceleration on Earth. So the equivalence principles tell you that a laboratory on Earth, this is Earth, you are in the laboratory on Earth, you are experiencing the gravity acceleration, G, which helps you to stand on your feet. If there was no acceleration towards the ground, you will just sort of float in the air. You will not stand on your feet like you do every day. So experiencing this acceleration or being in a rocket where the ground accelerates with an acceleration of G. This these two cases are totally equivalent according to the equivalence principle. And so now in my rocket, remember I had a clock here, clock A, and I had a clock here, clock B. Well, I can do the same now in my laboratory on Earth. Clock A, clock B. We conclude in the rocket that I have it here. Yes, that tau B will be equal to tau A 1 1 plus the acceleration time the difference, the spatial difference, delta x. So this is delta x, and the acceleration now is, it is still a here. The acceleration is a. Now on Earth, the acceleration is g, and the difference, the spatial difference is just a difference of height, h. And so I can say that tau b equal tau a 1 plus g times h. Or in infinitesimal step, d tau b equal d tau a 1 plus g h. Okay, and now with this infinitesimal element, d tau b, we can ask ourselves the very last question, now that we see that those cases are equivalent. Okay, now we can ask ourselves, this is Earth. What is the time difference between a clock on Earth, that will be tau A, and a clock radially very far, actually radius goes to infinity, on clock B? Okay, what will be the difference between clock A and clock B? And we know that G is approximately 10 meters per second square on the surface of the Earth, but we don't know what is G here and G here. I mean, we do, but what I mean is that G is going to decrease until you feel no more acceleration of gravity infinitely far from Earth. You will never get attracted by the Earth. Okay. The problem here is that I said that the equivalence principle only holds for small enough region. So now we have to do sort of a mathematical trick. We have to consider a laboratory here, next to another laboratory, next to another laboratory, next to another laboratory, with each clock A, clock B, clock A, clock B, clock A, clock B, clock A, clock B, etc. The height of the laboratory is still h. So I have sort of a graduation of 1h, 2h, 3h, 4h, 5h, that's 6h. Okay, and I can each time this clock is equal to this clock, and I can only compare clock A with clock B. Then my clock B is equal to this clock A. I compare clock A with clock B again. Then my clock B is equal to my clock A. Then I compare clock A with clock B, clock A with clock B, clock A with clock B, and I do that in infinity of time, which mathematically reads as d tau P equal d tau A1 plus the sum from h equals 0 to h equal infinity g of r. Yeah, and now I should call this h and r here are the same. They label a radial distance. So now this I could just, I didn't see that coming. Okay, r, and now this is 6r. Okay, and those small steps are delta r. So this is 6. This is actually 6 delta r. Okay. So I have to do the sum of gr delta r, and this I didn't invent it. It comes from here. It comes from everything that we derived mathematically from before. Okay. And now I will take the limit delta r to 0. So here delta r, we can say that it was maybe, we can say that delta r was maybe 2 meters. I mean, usually the ceiling is, yeah, maybe not 2 meters, maybe, okay, 2.5 meters. Now I want to take the smallest distance possible. So I will take the limit delta r equal to 0. And thanks to this, I can integrate. I can do a continuous sum instead of a discrete sum. So now I have that d tau b equal d tau a 1 plus the integral from r equal 0 to r equal infinity g of r dr. So yes, dr, because if delta r, if I take the limit of delta r to 0, I can just rewrite this dr, an infinitesimal element of radial distance, dr. Okay, but This integral over the gravitational acceleration g, it's nothing else than the gravitational potential. This you have to recall it from your classical Newtonian mechanic. You can write Tito B equal Tito A 1 plus phi of r infinity. Phi is the gravitational potential minus phi of r 0, right? But we said before, and I'm saying it again, that the gravitational potential infinitely far away from its source, well, we know that this equals 0. You will never feel any gravitational potential if you're infinitely far from Earth or from the sun or from a black hole. Okay, so this equals 0. Now by convention, Toby was the clock infinitely far out here. So by convention, we will say that this is sort of universal time, dt. The proper time stay the proper time dτ, and we have 1 minus phi of r, and we are done. We just demonstrated that the gravitational potential, oh, sorry, okay. The gravitational potential, which has for source, we know that gravity is triggered by mass, so has for source mass, but it can be any gravitational potential, not only a spherically symmetric. Yes, we now see that gravitational potential curve space time. So from mathematical notion of special relativity to the equivalence principle, we see that we can totally treat gravitational field as curving space-time. So it's either this image where space-time fabric is sort of this. So mass curve the fabric of space-time. Or let me consider one last concept, is that actually if you want to draw a space-time diagram, but we're no longer in flat space-time, we have now a massive object. So we have Earth. Earth is evolving in time, and someone on Earth has his light cone. Light cone gives you the direction of your future. So it gives you your time axis, t, x. So someone on Earth has a very smally, much more smally tilted light cone that I draw here, but I have to draw it very tilted so you can see. Then someone very in outer space. It would have his time going like this, and yes, so we see that space and time near a massive body are curved. And yeah, if I drew time like this, I guess that yeah, it's not perfect. I guess that I should more, yeah, I should conserve. Okay, so I drew time from left to right. So actually my light cones, I should draw them like this. So we see that here it's conserved. Time still flow from past to future or from left to right. But here the light cone are very uh, are a little bit tilted, and so this is why this is why an apple fall on Earth, or why the moon orbits around the Earth. It's because Earth, which is quite a very massive object for us at least, is carrying space-time. Yes. Okay. Well, it was not an easy task to understand and to explain why, in first place, should we talk about gravity as a curvature of fabric of the space-time, but I'm very happy that now it's done. And in the future videos, we will talk about the Riemann tensor, which is a mathematical tool that helps us to describe the curvature of space-time. So thank you very much for watching. I hope it was clear. If there is anything you want to add in the comments, please feel free. I would love to read some comments. And see you soon. Thank you for watching. Bye.